In this video, we're going to look at geometric sequences. A geometric sequence is a sequence that can be defined recursively as an plus 1 is equal to r times an. So let's compute a few terms. a1 is equal to r times a0. a2 is equal to r times the previous term, which is a1, but a1 is r times a0. So we get r times r a0, so we get a2 is equal to r squared a0. Now let's look at a3. a3 is equal to r times the previous term, which is a2, but we computed a2 to be r squared a0. So a3 is equal to r times a2, which is r squared a0. That gives us r cubed. We begin to see a pattern. So similarly, a4, and the pattern of course is when we have a subscript 3 here, we have an exponent 3 here. So an would be r to the n a0. That's the pattern we're seeking. a4 is going to be r times the previous term, which is a3. But a3 is r cubed a0. So we get a4 is equal to r times r cubed times a0. This is equal to r to the 4 times a0. So let's list these terms and see the pattern. a1 is equal to r times a0. a2 is equal to r squared times a0. a3 is equal to r cubed a0. And a subscript n, an is equal to r to the n a0. This is a general term. So we can define a geometric sequence as an is equal to a times r to the n, where n is larger or equal to 0. Or we can define it as an is equal to a times r to the n minus 1 for n larger or equal to 1. Here are some examples of geometric sequences. For example, an is equal to 2 times 2/3 to the power of n, where n is larger or equal to 0. Where this is the a is 2, it's just a constant, and the common ratio is the thing in the brackets, is the thing that's being exponentiated, raised to the power of n. So this is the common ratio, which is 2/3. All right, so graph the following sequences and also discuss their convergence. So looking at the first one, we have an is equal to 1/2 to the n goes from 0 to infinity. The second sequence is an is equal to 2 to the n, and n goes from 0 to infinity. And the third sequence, we have an is equal to minus 3 over 4 to the n, and n goes from 0 to infinity. So looking at part A, we have an is equal to 1/2 to the power of n. So let's compute a few terms. a0 is going to be 1/2 to the 0. Anything to the power of 0 is 1. a1 is equal to 1/2 to the 1. That's going to be 1/2. a2 is equal to 1/2 squared. That's 1/4. a3 is 1/8. So we can see that the common ratio, r, is equal to 1/2. And since r is less than 1, the terms of the geometric sequence are getting smaller and smaller, because a fraction that is in magnitude less than 1, when we raise it to a high power, it gets smaller and smaller. And of course, the reason is because every term is 1/2 the previous term, 1/2 an, if we define it recursively. So the sequence 1/2 to the n, as n goes from 0 to infinity, converges to 0. And we can even take the limit to show this. The limit as n goes to infinity of 1/2 to the n is equal to limit as n goes to infinity of 1 divided by 2 to the n, and 1 divided by 2 to the n, and 2 to the n grows infinitely large, and the numerator is just a constant 1, so the ratio approaches 0. The sequence now converges to 0. All right, and of course, this sequence is monotonically decreasing. We start at 1, that's a0, 1/2, 1/4, and every term is 1/2 the previous term, so it's definitely monotonically decreasing, and it converges to 0. So here's the graph. We can see there's our a0 here, so that's a0. And this is A1, which is 1/2. There's A2, 1/4. A3, which is, I guess, 1/8. A4, which is 1/16. And A5, 1/32. And you can see how it's approaching y equals 0, approaching the x-axis, basically. So the limit, the limit as n goes to infinity of 1/2 to the n is equal to 0. The sequence an converges to 0. Converges to 0. And we see that graphically as well. Now, let's look at the second sequence. Here we have Bn is equal to 2 to the n. Let's compute a few terms. Plugging n equals 0. B0 is equal to 2 to the 0, which is 1. B1 is equal to 2 to the 1, that's 2. B2 is equal to 2 squared, that's 4. And B3 is going to be 2 cubed, that's 8. And of course, it's just getting larger, larger, and larger. The reason is because the common ratio is 2, is bigger than 1. And because r is bigger than 1, the terms of the geometric sequence are getting progressively larger, as every term is twice the previous term, because bn plus 1 is equal to 2 times bn. Every successive term is twice the previous term. For this reason, the sequence 2 to the n, as n goes from 0 to infinity, diverges to infinity. So essentially, the limit as n goes to infinity of bn is equal to limit as n goes to infinity of 2 to the n. This is equal to goes to infinity. And of course, the sequence is also monotonically increasing. So bn, and the reason is clear, is because every term is twice the previous one. So bn is monotonically increasing. And this sequence diverges to infinity. So bn is equal to 2 to the n. And the sequence bn diverges to infinity. So let's see it graphically. So we can see that b0 is equal to 2 to the 0, that's 1. So this is b0, this is the first term. b1, b2, that's 2 squared, that's 4. b3, b4. And so basically, you can see how bn equals 2 to the n. Because the common ratio, r equals 2, is larger than 1, this sequence diverges to infinity. And it's monotonically increasing, of course, because every term is twice the previous one. Compare this to the previous one, where the common ratio was 1/2. And it's because of this, the common ratio is 1/2. When you raise a fraction that's less than 1, raise it to high power, it gets smaller and smaller and eventually approaches 0. All right, let's look at another example, number C. So here we have Cn is equal to minus 3 over 4 to the power of n. Let's compute a few terms. C0 is equal to minus 3 over 4 to the power of 0. That's just 1. Anything to the power of 0 is 1. C1 is equal to minus 3 over 4 to the power of 1, minus 3/4. C2 is equal to minus 3 over 4 squared. That's 9/16. And C3 is equal to minus 27 divided by 64. Because that's minus 3 cubed, which is minus 27, divided by 4 cubed, which is 64. So let's rewrite Cn is equal to minus 3 over 4 to the power of n. Let's rewrite this as negative 1 to the n times 3 over 4 to the n. Why do we rewrite it in this way? So that we can analyze it. Notice that the factor negative 1 to the n oscillates. It oscillates between 1 and negative 1. Oscillates between negative 1 and 1. And the reason is because negative 1 raised to an odd power is negative 1, is equal to minus 1, and negative 1 raised to an even power is plus 1. So 3/4 to the n, 3 over 4 to the n, decreases to 0 because the fraction, the common ratio of 3/4 is less than 1. So it decreases to 0 because every term is 3/4 the magnitude of the previous term. So by the squeeze law, we're going to show that the limit of this sequence is 0. So let's start with the sequence that we're given. Minus 1 to the n times 3 over 4 to the power of n. But we know that negative 1 to the n is less than 1. So 1 times 3 over 4 to the n larger than negative 1 times 3 over 4 to the power of n. Now let's take the limit as n goes to infinity, limit as n goes to infinity, and limit as n goes to infinity. This limit is going to be 0. Why is that? Because the common ratio is 3/4. A fraction less than 1 raised to infinity is going to be 0 because it gets progressively smaller and smaller. And the ratio of 3/4 over to the n is, for the same reason, is going to go to 0. By squeeze law, the sequence negative 1 to the n times 3 over 4 to the n is going to approach 0, but always write the reason for it. I'll just abbreviate it because there's no space, but in an exam you should write it out in full. So it's 0 by squeeze law. All right, so let's look at the graph of this. So we have Cn is equal to minus 3 over 4 to the n, and that's equal to minus 1 to the n times 3 over 4 to the n. The common ratio is less than 1. And that's why this sequence converges. This sequence oscillates and converges to 0 as n goes to infinity. So look at this. This is A0 here. A0 is 1. A1 now is negative, is here. And A2. A2 is positive. A3. A4. Notice how it's switching from positive to negative, but its magnitude is getting smaller and smaller. A5. A6. A7. A8, and progressively these terms approach 0. So you can see how if we were to trace a curve through these points, you can kind of see what's happening. So let's do that. A0 goes to A1, A2, A3, A4, to A5, A6, A7, A8, and you can see how it's basically approaching 0 as n goes to infinity. Now, this sequence is not monotonic. This sequence is oscillatory. What makes it oscillatory is the factor negative 1 to the n. This is what causes the oscillatory behavior. All right, so this sequence converges to 0, and we use the squeeze law to prove that. Now, let's go over some theory pertaining to geometric sequences. So basically what we have is the limit as n goes to infinity of r to the n. This is going to be 0 when absolute value of the ratio, absolute value of r, is less than 1. Or equivalently, when r is between 1 and negative 1. This is equal to 1 if r equals 1. Incidentally, a sequence would converge because all the terms would just be 1, so it converges to 1. And the limit of r to the n would be infinity if r is bigger than 1. It would not exist when r would be less than or equal to minus 1. Let's give an example of this last one, because the examples that we didn't have this particular example. So let's look at that. For example, if an is equal to minus 2 to the n. If we rewrite this, this is negative 1 to the n times 2 to the n. So you can see when n is even, an is going to be minus 1 to the power of, say, 100. That's plus 1 times 2 to the 100. That's approaching infinity. An approaches infinity for even integers. For odd integers, an approaches minus infinity. So these two are, of course, different. So we can't say diverges to infinity, and we can't say diverges to minus infinity because it's oscillating between infinity and minus infinity. In any case, we say this sequence diverges. So we say an diverges. Now we have a line diagram that shows all the values of r for which the sequence diverges. If r is bigger than 1, then the sequence diverges. If r is between 1 and negative 1, the sequence converges. And so for values of r between 1 and negative 1, the sequence converges. And when r is less than or equal to minus 1, which is the last example we looked at, when an is equal to minus 2 to the n, where the r value is minus 2, which is less than minus 1, the sequence diverges. All right, thank you.